This is the second lecture of week 8, and we're going to cover log transformation. So in the previous lecture, we talked about one of two ways of modeling nonlinear relationship, which was using polynomials of x variables. In this lecture, we're going to talk about the second approach of modeling nonlinear relationship, which is using log transformation. We're going to talk about 3 different cases of log transformation and how we interpret the coefficients. So before we get into all the math, I just want to point out the basic mathematical formula that we're going to use, which is log of x plus change in x minus log of x can be approximated by change in x over x. Numerically, this can be seen, for instance, log of 1.01, which can be rewritten as 1 plus 1 over 100. So this is writing it in this form. So in this case, change of x is 1 and x is 100. So this can be approximated by 1 over 100. In reality, if you do log of 1.01, it gives you 0.009, which is about 0.01. So this formula shows that this can be approximated by change of x over x. And this is the same case for 1.1 as well. This can be rewritten as 1 plus 1 over 10. And our formula says that this can be approximated by 1 over 10, or which is 0.1. And when you calculate log of 1.1, it's actually 0.09, which is close to 0.1. So we're going to talk about 3 different cases of log transformation. The first is called linear log, where you log transform the independent variable x. The second case is called log linear, which is when you log transform the dependent variable y. The last case is called log-log, where you transform both the dependent and independent variables. So in each of these cases, the interpretation of the coefficient beta 1 changes. And we're going to talk about why we interpret a certain way and how to interpret it. A lot of these will be involving math, and you don't need to memorize the math formulas, but it's important to understand how to interpret these coefficients and why it's interpreted that way. So let's start off with the linear log case. First, we're going to start off with the basic linear log function, which is y is equal to beta 0 plus beta 1 log of x. And let's say that x changes by small amount, which also makes the y change by small amount. When you subtract this second function from the first function, you have y cancel out on the left-hand side, and you have change in y left. And then beta 0 also cancels out, and you have this function called beta 1 times log of x plus change of x minus log of x. We know that from previous math formula that this is equal to change of x over x. And so we can substitute that in here, which gives you this function of change in y can be approximated by beta 1 times change of x over x. Rearranging this would give you beta 1 is approximated by change in y over change in x over x. So basically, you're dividing each left-hand side and right-hand side by change in x over x, and then it gives you this formula. So this formula shows you that the coefficient beta 1 can be approximated by change in y over change in x over x. I think the easier way to interpret this is by rearranging this. So let's multiply both left-hand side and right-hand side by change of x over x. So now we have this formula. We also know that 100 times change of x over x is a percentage of change in x. And that's because change in x over x itself, so for instance, if you change x by 1 and your original x was say 100, that gives you 0.01, but then if you multiply this by 100, that gives you 1%. So if you multiply the left-hand side, say 100 over 100, then we can rearrange this to show that basically 100 times change over x over x. So when x changes by 1%, then y would change by 1 over x times beta 1. Or 1 over 100 times beta 1. So let's look at the example of trying to estimate the relationship between test score and district income. Let's say that we want to, instead of using level of district income, we want to use log of district income. So first we have to log transform the district income, and then we can estimate the OLS model by running the regression of test score on log of district income. If you run the regression in data, it will give you the coefficients of intercept as well as the coefficient for log income. The way you interpret this 36.42 coefficient is that if income increases by 1%, the test score would increase by 1 over 100 times 36.42, which is 0.3642. Again, the way you interpret the coefficient would be if district income increases by 1%, the test score would increase by 0.36. Let's compare how the log transformation perform against the polynomial model. So in this graph, we're plotting the data points as well as the linear log regression model that we just estimated and the cubic regression line. It looks like just by looking at it, both of the lines are fitting the data pretty well. Because both of these regression models have the same dependent variable, which is the test score, we can actually compare the adjusted R-square to choose the model that better fits the data. So whichever model that has a higher adjusted R-square can be chosen because it fits the data better. Now we're going to move on to the second case of log linear model. In log linear model, we're going to log transform the dependent variable y. As in the previous case, we're going to first start off with the basic log linear model and then change x, which will cause change y. As we've shown in the previous case, we're going to subtract the basic model from the change model. And in this case, on the left-hand side, this will give us log of y plus change in y minus log of y. And on the right-hand side, beta 0 cancels out and beta 1 x cancels out, so all you have left is beta 1 times change in x. We know that this can be estimated by change in y over y, so this formula becomes change in y over y can be estimated beta 1 change in x, and then once you rearrange things by multiplying both sides by 1 over change in x, we get this final formula. So this formula shows the coefficient can be written as this, and I'm going to rearrange this to make it easier for us to interpret. So I'm going to rearrange it by multiplying each left-hand side and right-hand side by change in x. This gives me that beta 1 times change in x is equal to change in y over y. We know that 100 times change y in y is percentage change in y. So I'm going to multiply each side by 100. And this function indicates that if I change x by 1 unit, the y variable, or y would change by 100 times beta 1%. Let's look at the examples of looking at the relationship between earnings and age. Let's say that we believe there's some sort of a nonlinear relationship between earnings and age. And so we log transform the earnings and run OLS regression against age, and we get this coefficient 0.0095. The way to interpret this coefficient is that if age increases by 1, the earnings would increase by 0.0095 times 100%, or 0.95%. In other words, for each additional year of age, earnings are predicted to increase by almost 1% in our model. So let's look at the last log transformation case, which is a log-log case. So in log-log case, we're log transforming both the dependent variable and the independent variable. And we're going to follow the same steps as before. So we start off with the basic log-log function, and then we're going to change x by some small amount, which is going to cause y to change by some amount. And then we're going to subtract b from a. And doing that would give you this on the left-hand side. And then on the right-hand side, the beta 0 cancels out, and you're left with beta 1 times log of x plus change in x minus log of x. We know that this part is equal to this, and we know that this can also be estimated by this. So rearranging this would give you beta 1 is equal to change in y over y and over change in x over x. So as in previous case, I'm going to rearrange this function a little bit. So multiplying the left-hand side and the right-hand side by change in x over x, which gives me this function. And then I'm going to multiply both sides by 100. So this shows that when x increases by 1%, then y would also increase by beta 1%. So log-log function usually has an interpretation of elasticity because it gives you, the coefficient actually tells you how much y changes in percent when x changes by 1%. So let's go back to our example of measuring the relationship between test score and district income. We want to estimate the log-log function. So in our case, we're going to log transform both the test score and district income and run the OLS. This gives us a coefficient of 0.0554. How do you interpret this coefficient? This coefficient shows that if income increases by 1%, the test score would increase by 0.0554%. So let's say in our example that there is a district with per capita income of 10,000, and this district's per capita income increases to 11,000 or by 10%. In this case, our model predicts that the test score would increase by 0.0554 times 10%, which is 0.554%. So if the test score was 650 to begin with, this corresponds to 3.6 points, meaning that if the income of the district with $10,000 per capita increases by 10%, the test score in that district would go from 650 to 653.6 points. Let's look at how the log linear model performs compared to log model. So when you plot the log test score against the district income with these lines, you can see it seems like the log regression model seems to perform better. Instead of just using visual observation, we can also use the adjusted R-square to choose a model that better fits the data. So whichever regression model that has a higher adjusted R-square fits the data better. One thing to notice is that in log linear model, because our graph has log transformed test score, the model actually becomes straight line. The last thing is that if you want to compare the log model or log linear model to the previous model, such as cubic model or linear log model, we cannot just look at the adjusted R-square because these models have different dependent variable. So the interpretation of adjusted R-square is how much y changes or how much of variation in y is explained by changes in x. But in our case of cubic or linear log model, the dependent variable is just y, whereas in our log linear or log model, the dependent variable is log of y. So the adjusted R-square actually, you cannot compare the adjusted R-square of the cubic or linear log model where the dependent variable is y to the adjusted R-square of log linear or log model where the dependent variable is log of y. So to summarize, we have talked about 3 different cases of log transformation and how to interpret coefficient for each case. So how do you decide which log transformation to implement? So this could be guided by plotting the predicted value, meaning that you plot the log transformed line to the data and see which model fits the best and choose the model that way. Or you can conduct some sort of a test. So looking at the adjusted R-square and comparing them if the models have the same dependent variables. Or you can carry out a t-test. So for instance, if you're doing a log model and you can look at the coefficient of log x and see if beta 1 is statistically significant or not. And if it's statistically significant, then you may want to keep the model. Lastly, as I mentioned in the previous lecture, the way you choose the log transformation model can be very subjective. So you should always rely on your expert knowledge or your common sense to pick the model.